Let's study electric field due to an electric dipole and its surrounding. Say we are given with an electric dipole placed in a coordinate system. At the origin of coordinate system, we have placed a dipole here, and as we already discussed, a dipole is generally represented by an arrow with the head of arrow located in the position of the positive charge of the dipole, and its tail is at the location of negative charge of the dipole. Now in this situation, say we are required to find the electric field strength at a position P, at a point P, which is located at the polar coordinates with a radial distance r and polar angle theta with the equator or positive direction of x-axis. Then in this situation we can see, due to the positive charge at point P, the electric field will exist in the direction away from the charge because it is positive, so we can denote it E due to the positive charge. And here, due to the negative charge, electric field will exist, which is E due to negative charge directed towards the negative charge, and the resulting electric field, which is the vector sum of these two fields, is the net electric field we can denote at point P. And as we are taking the position coordinate of P in polar form, that is r and theta, so here we resolve these electric fields along radial direction as well as the transverse direction. The direction of position vector of point with respect to origin we call radial direction, and the direction perpendicular to the radial direction we call transverse direction. Now in this situation, here we can see if the angles of E due to positive and E due to negative with the transverse direction are alpha and beta, then we can easily calculate the radial component of electric field, which is denoted as ER, and transverse component of electric field, which is E theta due to E plus and E minus. So here we can write a radial electric field at point P is this ER we can directly give as the sum of the components of E plus and E minus along radial direction. So this we can see these are in opposite directions, so it will be E plus sine alpha minus E negative sine beta. Similarly, we can find out transverse electric field at point P is thus given as E theta. Transverse component is denoted by E theta, which is perpendicular to the radial direction. Here it can be given by sum of the two components because these are in same direction, so it can be written as E positive cos alpha plus E negative cos beta. Now in this situation, when the two components radial and transverse are calculated by substitution of the values of E positive, E negative, sin alpha, sin beta, cos beta, and the final results I'm writing here, which are quite important for various applications. Final results of ER and E theta are, these results will get ER we are going to get, it will be 2 kp sin theta by r cube, and the transverse component will get as kp cos theta by r cube. So be careful about both of these results, and using this we can write this implies net electric field at point P is this E net we can write by the summation of this E theta and ER, as these are right angle to each other, it will be ER square plus E theta square. If you substitute the values of ER, E theta here, the value of net electric field at point P will get as Kp by R cube root of 1 plus 3 sin square theta. Many students generally do a mistake here, just they keep as it is these results in mind and sometimes in different problems we are given with the point P, which is located at a distance r, but the angle of position vector is not given with the equator of dipole, it is given from the axis of dipole. If the angle given in the problem is this, in that case these trigonometric terms will get swapped, like here instead of sin theta, cos theta will be there, here sin theta will be there, and here cos theta will be there. So just be careful while using these results in your different applications. It all depends on whether the given angle is from the equator of dipole, that is the line perpendicular to a dipole passing through its center, or the angle is given from the axis of dipole. Let's continue with the direction of net electric field in surrounding of a dipole. Here you can see if this is a dipole and we wish to calculate the electric field, net electric field at a point P located at a distance r from the center of dipole and at an angle theta from the equatorial line of the dipole. In this situation, we know that due to the positive charge, electric field is away from it, and due to negative charge, it is toward from it. And just by virtually visualizing the directions due to plus and minus, we can see positive charge is closer to point P. That means the effect of positive charge at P will be more compared to negative charge. So net electric field at point P is away from the dipole. That means its radial direction of electric field is away from the center of dipole, and due to positive and negative resulting perpendicular component, when we calculate, that is transverse component, this will be in this direction, which is E theta. Now if we take the resultant of these two, net electric field will exist in this direction, which is making say an angle phi with the radial direction. In this situation, angle phi can be easily calculated as tan phi is equals to E theta upon ER, and if we substitute the values of E theta and ER which we have calculated in the previous sheet, the result we are getting is half cot theta. Now in this situation we are getting the value of phi. This is actually phi which I am using. So this phi can be written as tan inverse of half cot theta, which is the angle made by the net electric field from the radial direction. So net slope of electric field can be calculated as theta minus phi, because theta is the angle in which the radial direction of point P exists, and phi is the opposite angle from the radial direction where net electric field exists. In this situation, you must be very careful about analyzing the directions of ER and E theta. That's also quite useful. Like in various cases, I just take up some example, like if we are given with a dipole placed in a horizontal alignment, then this orientation, if I wish to calculate the electric field at this point, here you can see this positive and this negative, and at point P you can see positive end is closer to this point. That means the net electric field at this point in radial direction will be away from it, that is ER, and positive will apply an electric field in this direction, negative in this direction. So radial, the electric field perpendicular to the radial direction, transverse electric field will exist in this direction. Similarly, say we are given with a dipole which is placed like this, and in this orientation, say we are required to find the directions of electric field at this point P due to this dipole. Here we can see out of negative and positive ends, negative end is closer to point P, so effect of negative end is more, so the radial electric field will exist in the direction toward the dipole, and due to this negative and electric field will be in this direction, due to positive it is in this direction, so we can see a transverse electric field exists in this direction. So I hope you are clear with the way how we are calculating directions of ER and E theta in this case or in this case. We can have another example, like say we are given with a dipole in a vertical alignment and we are required to find the electric field at this point P. then we can see out of positive and negative end which end is closer to point P. Here you can see that negative end is closer. That means effect of negative charge is more at P. So radial direction will be toward the dipole, it is ER. And due to this negative end, electric field will be in this direction. Due to positive, it is in this direction. So the resultant of the two fields in the direction perpendicular to radial direction will be E theta, and it is in this direction. This is the way how we find out the actual directions of ER and E theta rather than independently calculating the values. In various qualitative analysis, this methodology to find the direction will also help us.